Okay, graphical analysis of nonlinear circuits. Circuit that contains at least one nonlinear element. Such circuit is described by the system of nonlinear equations. Solution of such system is very complicated story, and we will not discuss this story in general. We will discuss only two-dimensional system and a very practical one. So we have two equations. In such case, we may solve them graphically. We assume that our I relationships of nonlinear elements are approximated by piecewise linear approximation, PWL, and we start with the connection of two elements. One of them, at least one of them, is nonlinear. Obviously, it is impossible to find the equivalent resistance as one of the elements is nonlinear, described by its equation. Then we may find the total I relationship by adding relationships of individual elements. How? In case of a series connection, we have the same current flowing through both elements, and voltage is sum of voltages. Simply we have to add, for given currents, we have to add voltages. For these exemplary two curves that we have here, then for this current we have two voltage. We have to add this current, two voltage, we have to add to this voltage we have add voltages, and then we obtain the I relationship designated by these points as depicted here by a black line. Very similar reason can be repeated for parallel connection. Now we have the same voltage and current is sum of two currents. Then we have to add following the vertical axis, we have to add currents. So we have to, at these points, we have to add these currents to obtain the total IU relationship of these two elements connected in parallel as depicted here, black line. Now we are ready to discuss a graphical analysis first of a mesh circuit, single loop circuit built of voltage source, linear resistor and nonlinear resistor. This circuit is described by Kirchhoff's voltage law, element equation and Ohm's law. And these equations are here. So this is equation of nonlinear element. Then from Kirchhoff's voltage law and Ohm's law, we may express current that flows through a resistor by its voltage. And the first equation that describes nonlinear element is already present on this plot. Now let us draw this line that corresponds to this equation. So this line crosses the horizontal axis here and the vertical axis here. Okay, let me connect these 2 points, and this is the line that crosses nonlinear element here, and this is our solution, this so-called Q point. On the next slide, repeated. A Q point or quiescent point, it is solution of our problem. Okay, this was very simple loop circuit. This reasoning can be generalized now to complex circuit. However, this complexity is rather in its linear part. I mean, we have a complex linear part, and then we have one or maybe few, 2 or 3 nonlinear elements, such that we may replace them by a single one, following the reasoning that I have just discussed before. Then we may transform our complex circuit to single loop circuit. We may solve this single loop circuit by graphical method as described before, and then if we are interested in currents or voltages inside a linear part, we simply have to separate nonlinear element by means of separation principle, as we have already calculated voltage. This voltage is Q point voltage. Okay, let me illustrate this strategy, this algorithm by means of this simple problem. We have one nonlinear element, and then we have a linear part which is here. This linear part has to be replaced by a Thevenin equivalent. That is trivial, so its voltage source is 8 and resistance, total resistance that's seen from terminals of nonlinear element is 10/3. Okay, now we have, at the right side, we have given the I relationship of nonlinear element. We have to draw characteristic of the load line. So this characteristic crosses the voltage axis here, but unfortunately, the point that this line crosses the vertical axis is somewhere up here. So we have to accept that delta U is, let's say, 1 volt, and we may calculate delta I very easily, like that. So for delta U equal 1 volt, delta I is 0.3, and we have this point designated. So now we are ready to connect these 2 points to find the Q point, the solution of our nonlinear circuit. I mean, our solution that we are looking for is not the voltage across the nonlinear element, it is power dissipated by a voltage source. Then we have to apply the separation principle. This is repeated at this quiescent point. Our voltage that we will use for separation is 725. Okay, this 725 separates this nonlinear element from a linear part, and the rest is solution analysis of linear circuit. From this analysis we will find that power which is supplied by a voltage source to this circuit is 11.4 volt. More exemplary problems in the lecture. Thank you for your attention.